Dear friends, I am Dr. R.B.Solanki from Vasantrao Naik Arts, Science and Commerce, College Shahada, Department of Chemistry. We are studying the chapter solutions. Already we have discussed about the types of solutions. Now here the next topic is different ways of expressing concentration of the solutions. So here the concentration can be expressed in different types of concentrating terms, that is molality, molarity, normality, weight by mass percent, weight by volume percent, mole fractions. So these are the different ways for expressing the concentrations. Now, the relative amount of substance present in the solution of a mixture is known as its concentration. There are various ways to express the concentrations of the solutions. So consider the binary solution. Binary means the solution of two components. One is solute and other is solvent. So consider the binary solution of two components A and B. Here B is solute, A is solvent. Let small na and small nb are the number of moles of capital A and B, that is the solvent and solute respectively. Wa and Wb are the weights of A and B, that is solvent and solute respectively. Va and Vb are the volumes of A and B in liters, and capital V is total volume of the solution in liters. So now we have to consider one by one concentrations of the solutions, how they are expressed in different ways. So first is molarity. Its symbol is capital M. It is the number of moles of solute per liter of solvent given as the molarity of the B in the solution, and it is given by Mb is equal to Nb divided by V. So this is the molarity. Now second term for expressing the solution concentration is molality. Symbol is small m. It is the number of moles of solute per 1000 grams of solvent. The molality of the B, that is solute, is expressed as Mb is equal to Nb divided by 1000 grams of solvent or 1 kilogram of solvent. Third term is the normality. Its symbol is capital N. It is the number of moles of gram equivalents of the solute dissolved in 1 liter of solution. It is expressed in gram equivalents per liter. So this is the third term for expressing the normality, that is the concentration in terms of normality. Fourth is weight or mass percent, that is W by W. Here, when the concentration is expressed in terms of fixed weight, then it is expressed in terms of weight percent. It is defined as the amount of solute present in the 100 grams of solution. And next is, that is fifth, mass by volume, weight to volume. Concentration expressed on the basis of fixed volume, then it is expressed in terms of mass by volume, defined as amount of solute in grams present in 100 ml of solution. So here we are expressing concentrations in terms of different units. The sixth term for the expressing concentration is volume percent. Here concentration expressed in terms of fixed volume either of the solution or of the solvent alone. It is defined as the volume of the solute present in 100 ml of solution. And the most important term expressing the concentration is the mole fraction, that is 7th. This is expressed in terms of capital N or capital X. Here Na and Nb are the mole fractions of solute and solvent. Now the mole fraction is defined as the ratio of number of moles of solute or solvent to that of number of moles of solute and solvent. It is denoted by N or X. Let Wa and Wb are the masses of the solute and solvent respectively, and Ma and Mb are the molecular weights of solvent and solute respectively. So now number of moles of the solvent. We have to calculate number of moles of the solvent. It is denoted by small na. It is the ratio of weight of solvent to the molecular weight of solvent. So Wa divided by Ma. Similarly, number of moles of solute Nb is equal to weight of solute divided by molecular weight of solute, that is equal to Wa divided by Mb. Now, mole fractions of solute is denoted by Na. It is equal to Na divided by Na plus Nb, and mole fractions of solute Nb is equal to Nb divided by Na plus Nb. So, mole fractions is the number of that particular solute or solvent divided by total number of solute and solvent. So, this is the mole fractions. Now, we must know that Na plus Nb is equal to 1. It is always Na plus Nb is equal to 1. So, here we have to prove this Na plus Nb. So, Na plus Nb is equal to Na upon Na plus Nb, and Nb is equal to Nb divided by Na plus Nb. So, total sum is Na plus Nb divided by Na plus Nb, that is equal to 1. So, Na plus Nb is equal to 1. Hence, we can calculate Na or Nb from this equation. We have Na is equal to 1 minus Nb, or Nb is equal to 1 minus Na. So, in this way, we can calculate mole fractions. So, these are the 7 terms we can use for the expressing concentrations of the solution. Now friends, the next topic is Raoult's law and its limitations. This is the law which is discovered by Francois Marie Raoult 1830 to 1901. The statement for this law is the partial pressure of any volatile constituent of a solution at a constant temperature is equal to the vapor pressure of pure constituent multiplied by the mole fractions of that constituent in the solution. Mathematically, it is expressed as Pa is equal to Na into Pa0, where Na is the mole fraction of A, that is the solvent, and Pa0 is the pure vapor pressure of the component A, that is the pure solvent. Then similarly, Pb is equal to Nb into Pb0, where Nb is the mole fraction of A and Pb0 is the pure vapor pressure of the component B. If here the total vapor pressure we have to calculate, the partial vapor pressure of A is P is equal to N into Pa0 and Pb is equal to Nb into Pb0. If P is the total vapor pressure, then P is equal to Pa plus Pb. That is the sum of the two partial vapor pressure terms is the total vapor pressure. that is equal to Na into Pa0 plus Nb into Pb0. This law is major deciding factor whether the solution will be ideal or non-ideal. Ideal solution obeys Raoult's law at every range of concentration. When it does not obey, then the solution is non-ideal. Now, the main important term in this Raoult's law is vapor pressure. So, vapor pressure, we have to study here what is vapor pressure. So, the pressure exerted by vapors above the surface of liquid when the rate of evaporation is equal to the rate of condensation, that is equilibrium at a given temperature, is known as vapor pressure, and the vapor pressure of the liquid depends on nature of liquid and temperature. So in this way the Raoult's law is explained by the scientist Raoult in this chapter.